Today we'll take a look at one-to-one functions and their inverses. A quick review about one-to-one functions. We said that a function is one-to-one if each f of x value corresponds to exactly one x value in the domain. In other words, graphically they need to pass the horizontal line test in order to be one-to-one. We also said that if we have an always increasing function or an always decreasing function, we know that those must be one-to-one. We'll look at how to prove that algebraically a little bit. So to show that a function is one-to-one, we have to show that if the outputs are the same, then we would have had to have the same input that causes those outputs to be the same. So in other words, if f of x1 for some x1 value is equal to f of x2 for some different x2 value, then those x1 and x2 must be equal as well. To show a function is not one-to-one, that's a little bit easier. All we have to do is find two numbers, two different inputs that give the same output. In other words, look for one of those horizontal lines that breaks the rule for the horizontal line test. And that's going to be what we call a counterexample. If we can find something that disproves the claim that it's one-to-one, that's a counterexample. So take a look at these two. If we want to show that a function is one-to-one, like this one, 2 over x minus 3, then we start with f of x1 equals x2. We're assuming that we can choose two different inputs that give the same output, and we set them equal to each other, and then simplify. So try to solve for x1 or solve for x2. In this case, cross multiply or multiply both sides by their denominators. We get 2 times x2 minus 3 equals 2 times x1 minus 3, and you'll notice a lot of symmetry here often. So we can divide both sides by 2. We can add 6 to both sides. We can divide both sides, or actually we distribute it here, then added 6, then divide by 2. We're going to get that x2 is equal to x1. That means that this function is a one-to-one function. We started with two outputs with different x's, and we showed that the only way to get that is to have different inputs. That's kind of neat, right? But it's a little different if we're trying to show that it's one-to-one and it's not. So let's see what that looks like. Well, in this case, for part B, x squared minus 2, we just look for a counterexample. We're just looking for two different outputs that would have the same input. And one such counterexample, and you could graph this, right? You know that this is a quadratic function. This is going to be a parabola that's shifted down 2. You could choose any number of horizontal lines here, but we're choosing one with, for example, where x is 3, right? So we're choosing x equals 3 and x equals negative 3 to compare. And we'll compare those outputs. So plug negative 3 into the function and plug positive 3 in. You'll get negative 3 squared minus 2, that's 7. But if you plug positive 3 in, notice you're going to get exactly the same thing. So what that means is we chose two different inputs and we got the same output. In other words, if we went up to a height of 7 and drew a horizontal line, we would get an x of positive 3 and also an x of negative 3 that would cause the same output. That means that this is not a one-to-one function. A quick review of what we've discussed about inverse functions so far. Remember, we use that notation f negative 1 of x. That's not an exponent. That's just an unfortunate coincidence that it looks like that, right? But this is your inverse function notation. So this is f inverse of x, if it exists. And so the inverse, remember, when we find an inverse, it's still a function. So we take a function, find its inverse, and it's another function. So if y equals f of x, then the inverse would be f inverse of y, puts us back to the input that we started with. So in other words, we said that if we compose a function and its inverse, we should get back to where we started. So we take a function, plug it into its inverse, or the other way around, we should get back to x. So that's actually an algebraic way that we can check to see if functions are inverses, and we'll see that. And remember, we also said that if a function has domain D and range R, then the inverse function has those swapped. The domain of the inverse is actually R, and the range is actually D. We also said that a function only has an inverse if it's a one-to-one function. If not, right, if the function itself doesn't pass the horizontal line test, then the inverse wouldn't pass the vertical line test, and so it wouldn't be a function. So for the graph of the inverse, remember we said that's the reflection across the identity line y equals x, right? So we would take a look at our y equals x line and then reflect the original graph across that line in order to see where the inverse would be. Now be extra careful, we mentioned this at the top, but remember that f inverse of x, that's not a reciprocal. That's not a negative exponent. These things are not the same, right? Please make sure that you don't accidentally do that. And again, a graphic there just to remind you. We've got a domain, a one-to-one function maps a domain to a range, and the inverse function maps it back. So if we compose, if we do both, we get back where we started. So how do we determine an inverse using algebra? It's actually pretty easy. All we have to do is take our function and write it as, if it's written as f of x equals whatever function, write it as y equals instead, and then switch every instance of x and y. So find every y and turn it into an x, find every x and turn it into a y. When you do that, that's creating an equation that describes the inverse instead of the original function. So once you've done that, you've got your inverse, but you're going to want to solve it for y so that you can write it in function form. So once you switch all the x's and y's, then solve for y. And once you've done that, just rewrite instead of y, write it as f inverse of x, and you're done. So we'll take a look at a few examples of that for these three functions, 3x plus 2, root 3 minus x plus 4, and x minus 1 squared minus 2. So for the first one, f of x, for 3x plus 2, we want to do domain and range and calculate the inverse. So the domain and range is a linear function. Both of those are all real numbers. So in order to write the inverse, we write f of x equals 3x plus 2. That's the function form we started with. Replace f of x with y, and then swap the x's and y's. So again, at this point, this is technically our inverse, but we want to isolate y. So we're going to solve for y. We're going to subtract 2 from both sides. We're going to divide by 3. And then we'll replace that y with the f inverse notation. So that is our inverse function. The inverse of 3x plus 2 is x minus 2 over 3. And you could, if you want, you could simplify that. You could divide both terms by 3 there. You could write that as 1/3 x minus 2/3. Sorry for the sloppy handwriting, which is another linear function. And that's, you can see that graphically when we go to sketch out both of those as well, right? 3x plus 2 is the original line in black. The one in blue is going to be the inverse. Those are both essentially linear functions, and they are reflected across that identity line, y equals x. Let's try a couple more, right? G of x, remember, was root 3 minus x plus 4. The domain and range is slightly more complex here because of that radical. You can review how to do that, but we know that the domain of the original function is up to and including 3, right? So negative infinity up to including 3. And the range then, if you think about what y values we could get, remember that radical is only going to be 0 or bigger, so the range is going to go from 4 up. Now the easy part is just flip those to determine the domain and range of the inverse function. Be careful, this is the way you want to do that. When you do it algebraically, you may be eliminating some of these issues, and we'll see that. So to actually find the inverse, let's do it. Write g of x as y. Swap the x's and y's, and then solve for y once again. So we did that. We're going to subtract 4 over. We're going to square both sides. We're going to subtract 3 over, and then we'll multiply everything by -1 to solve for y. And so this time, the inverse of a square root function was a quadratic function. That kind of makes sense. And then at this point, we end up with rewriting y as g inverse of x. We've got our inverse function. And then so looking at a quick graph, right, you could sketch out the graph of the radical function, the original one's in black here, reflected across that identity line, and we've got the inverse function. But notice the domain doesn't look quite the same, right? You would think that a quadratic function would have a domain of all real numbers, but this is not an entire parabola here like you would think it might be. And notice that's because we were only starting with half of the picture because of the radical domain issue, right? To make this radical function a function, we can't have a bottom half to it. That would make the vertical line test not work. And so when we reflect it, remember we're going to actually only end up with half of a parabola instead of an entire parabola. So that's why we need to stick with these original domain restrictions instead of just calculating the domain after we do the inverse. So let's take a look at one more. We've got x minus 1 squared minus 2. The domain of this one, we've listed it as 1 to infinity there, and the range is going from -2 to infinity. I actually don't know if that's true. That could be all real numbers here, right? We could use any number for x. but notice that the range is going to be limited. So let's investigate this. Is this true? Let's find out. When we go to find the inverse, then we can replace h of x with y, swap the x's and y's, and we can add 2 to both sides and compute from there. And it looks like we're going to end up with y equals the square root of x plus 2 plus 1, or h inverse of x, once we rewrite that notation. So that's kind of interesting here. You would think that the domain, and this is, so we kind of skipped over this piece. This is what's causing our domain to be limited, right? You would think that the domain of a parabola, once again, would be all real numbers. This time the graph in red is the original. But we had an artificial restriction written down in here. We said that, ignore the natural domain, we said that x has to be at least 1. And so that's what caused this limited domain to happen. And so by doing that, we're restricting our graph, we're restricting this function to be only half of a parabola. We have to do that because otherwise the parabola wouldn't be 1 to 1, so it wouldn't have an inverse function. But once we do make that restriction and we flip the domain and ranges, we reflect across the y equals x identity line, we get this nice radical function that is indeed a function. Let's take a look at another example here. We've got the function 3 over x minus 1 minus 2. We've got a lot of things to do here. This will probably be our last example. We'll try to determine if this is 1 to 1. If it is, determine the inverse. Look at the function and its inverse together. We'll look at their domain and ranges. And lastly, this new thing will show that if we compose a function and its inverse, we get the identity x again. And we can do that both ways. So let's do all those things. First, is it 1 to 1? Let's try that algebraically, right? We'd choose two different inputs, x1, x2, and plug those in to set equal those two outputs. And we're going to test to see if we get the same input or not. So add 2 to both sides. You can cross multiply here. You can divide by 3. We can add 1 to both sides, and it looks like if we were to end up with 2 of the same output, we would have had to start with the same input here. So that means that f is a 1 to 1 function. So since it's 1 to 1, it has an inverse. Let's try to determine what it is. Right? We write y equals, replace the x's with y's and y's with x's. So this is where we swapped. Excuse me, and then solve for y. So multiply both sides by this. Actually, add 2 first. It's probably easier. Add 2 to the left side, and then multiply both sides by y minus 1. Then, to solve for y, divide both sides by x plus 2. Or you can FOIL this out. That works too, right? This is like y times x plus 2 minus 1 times x plus 2. And then from there, we would go ahead and add the 1 times x plus 2 over, divide by x plus 2, and we've got our inverse function. This is a rational function now. That's kind of cool, right? We've got x plus 5 over x plus 2. So next, let's do a few things. Let's look at the graph of each. Let's look at the domain and range. You can just use Desmos to graph these two. I've copied them up here for convenience, right? You can just graph both of those two in Desmos and see what they look like. They do look like inverses of each other, right? They're reflections across that identity line. They're both rational functions. That's kind of neat. And so now, for domain and range, look for your original function. The only issue there is dividing by 0 there. We can't let x equal positive 1. So the domain is negative infinity to 1 and 1 to infinity union together. The range then is everything except the horizontal asymptote, which happens at y equals negative 2. So the range goes negative infinity to negative 2, union negative 2 to infinity. And just swap those for the domain and range of the inverse. And you can kind of see that graphically it matches, right? The domain for the inverse, we can't include negative 2. In other words, that horizontal asymptote became a vertical asymptote, and vice versa. It's kind of cool. Lastly, let's do a couple of things. Let's compose the function with its inverse both ways and see if we get x back, to test if it's actually the inverse function. And this gets a little bit messy, but it's not too bad. We're plugging the function f into its inverse function, so it's going to look something like this. Plugging that function in for both x's. Now, we've got a lot of algebra to do here to simplify. Combine negative 2 and 5 on the top, negative 2 and positive 2 on the bottom. And then, to simplify this complex fraction, multiply the top and the bottom by x minus 1. That's going to simplify really nicely when we distribute into 3 plus 3 times x minus 1 divided by 3. which we can actually simplify even further. If we distribute out that 3, combine our like terms, divide by 3, we get just x. So we're good. It looks like we have a function that when we plug the function into its inverse, we get x back. But technically, you'd have to test it both ways, right? So we could try it the other way too. Plug the inverse into the original function. So plug this inverse into the x in the original function, and we get something like this: 3 over x plus 5 over x plus 2 minus 1 minus 2. Simplify that too, try to solve it, reduce it down to just x. So multiply the top and the bottom by x plus 2. That's going to help clear out our complex fraction there. So we get x plus 5 minus the quantity x plus 2 on the bottom. On top, we just have 3 times x plus 2, leaving that minus 2 out until the end. Simplify that fraction. We've got, we can distribute a 3 there. We distributed the negative to the x and the 2 in that last step. And so we've got on top 3 times x plus 2. On the bottom, the x's are canceling here, so we have just a 3. So we can divide that 3 out, and we have x plus 2 minus 2, which is just x. So since we can show that both ways, we know that this is in fact the inverse function.